Hi everyone, my name is Ishin and today I'm excited to walk you through my amplified machine learning pipeline for predicting telecom customer churn. But more importantly, I will demonstrate how I can solve this business problem using a responsible AI framework, ensuring the model is not only highly accurate but also interpretable, fair, and ready for production. Today I will answer the two required prompts. First, how I applied responsible AI principles and fairness, including how I audited and mitigated bias. Second, how I improve model interpretability and how interpretability supports ethical decision making. Here's roadmap. I will start by defining the business problem and the metric strategy, then move into rigorous model validation, uncover the black box using explainable AI, focusing on model comparison, thresholding, global and local SHAP, address fairness and ethical considerations, and finally look at how this model survives in a live production environment. Let's start with the business context. In the telecom industry, acquiring a new customer is significantly more expensive than retaining an existing one. The task is to predict binary customer churn so the business can proactively intervene. Looking at the data, the biggest challenge is class imbalance. Roughly 73% of customers stay and 27% churn. This imbalance dictates entire modeling strategy moving forward. And according to the isolation forest anomaly detection, abnormal users are usually old customers with high consumption and long-term online use. The churn rate is extremely low, and they belong to the high net worth VIP group. I report multiple metrics: ROC-AUC for ranking quality and F1 precision recall for threshold-based decision quality. Because of this imbalance, optimizing for simple accuracy is a trap. A naive model predicting no churn for everyone would be 73% accurate, but practically useless. Instead, the primary metric is the F1 score. Why? In business context, a false negative, missing a churn customer, results in a permanent loss of recurring revenue. A false positive, giving an unnecessary discount, only costs a small promotional fee. F1 perfectly balances this trade-off, and I also monitor ROC-AUC as a secondary metric to ensure the model maintains excellent overall ranking capabilities. Also, threshold section is done on the validation set, and the test set is used once for final evaluation. I clean the data by dropping customer ID, mapping churn to 1 or 0 or 1, and converting total charges to numeric because it often contains blanks. Then I use a leakage-safe preprocessing pipeline. Numeric features get imputation and scaling. Categorical features get imputation and one-hot encoding with unknown categories handled safely. To guarantee the evaluation is trustworthy, I implemented a strict leakage-safe pipeline. I performed a 60-20-20 stratified split for train, validation, and test set. All decisions from hyperparameter tooling to threshold optimization and fairness mitigation were strictly made on the validation set. I used a robust column transformer to handle imputation, scaling, and one-hot encoding, ensuring the test set remained completely unseen until the final evaluation. This is the evidence-based model comparison stage. I benchmarked multiple candidate models under the same practical and report AUC, F1, accuracy, precision, and recall on the validation set, and including logistic regression, random forest, XGBoost, and light GBM. While I reported a full suite of metrics, light GBM emerged as final champion model. It achieved the optimal balance, delivering the highest F1 score when utilizing building class weight. Instead of blindly use the default 0.5 decision boundary, I leveraged precision recall curves to pinpoint the exact threshold that maximizes F1 score, ensuring capture as many high-risk customers as possible. On this slide, I'm explaining why threshold tuning matters in an imbalanced Churn problem. The model output probability spot operational decision requires a hard 0 or 1 label, and the default 0.5 threshold is rarely optimal. Here I swapped the decision threshold from 0 to 1 and track the F1 score. You can see the F1 score rises and peaks around a threshold of 0.56, which I mark with the red dashed line. So instead of using 0.5, I choose 0.56 based on the validation set, because it gives the best chance a balance between precision and recall for the Churn clause. The reason this is important is cost. In Churn retention, false negatives missing a customer who will Churn often cost more than false positives. So threshold tuning is a practical way to align the model's decision rule with business priorities and unlock this threshold before evaluating on the unseen test set and before deployment. This slide shows the final evaluation on the unseen test using the tuned threshold. At the top is the classification report and below is the confusion metric. From the confusion metric, we have 839 true negatives and 255 true positives. You can also see 196 false positives customers flagged as Churners who did not churn, and 119 false negatives customers who churned but were missed. For the Churn clause, which is clause 1, the model achieves about 0.57 precision, 0.68 recall, and 0.62 F1 score. This means I capture a substantial portion of actual Churners, which is important because missed Churners are costly. At the same time, I accept some false positives, which is a manageable trade-off in many retention settings because the cost of outreach is typically lower than losing a customer. Now I'll move to interpretability, which is the second required prompt. This slide summarizes my interpretability strategy. Global SHAP for top drivers, local SHAP waterfall for customer-level explanations, PDP or ICE for feature effect, and counterfactual for actionable intervention. This makes the model transparent and support ethical decision-making. This slide shows my evidence. The left is SHAP summary highlight top Churn drivers like contract type, tenure, and monthly charges. Right is a SHAP waterfall explains one customer's prediction by showing which features push risk up or down. And at the bottom, I include permutations importance as a consistency check. The slide shows PDP, ICE, and counterfactuals. PDP indicates tenure generally lower Churn risk, while higher monthly charges increase Churn risk. Both align with domain intuition. Then a counterfactual what-if shows actionability. A month-to-month customer had Churn probability 0.9569, and switching to a 2-year contract reduces it to 0.2059, about a 75% risk drop. The slide summarizes my fairness workflow: measure, diagnose, mitigate, and re-evaluate. I audit fairness on senior citizen and gender using DP difference and equalized odds difference. Because senior citizen shows the larger gap, I run a validation grilled search for a group threshold offset, selecting the offset that improves fairness while keeping F1 degradation small. Then I apply that mitigation on the test set and report before-after result. Senior citizen fairness improves. DP goes down. And EO goes down too. Gender gaps are already small and stay small, so I avoid overcorrection. AUC stays 0.8 while F1 drops slightly, showing a clear reported fairness performance trade-off. Ethically, FP wastes resources and can annoy customers. FN misses Churners and causes revenue loss. Group disparities matter ethically because uneven error rate can translate into disproportionate targeting or neglect of vulnerable groups. So I recommend safeguard first human in the loop review for high impact action such as large discount or aggressive interventions. Second, transparency and appeal mechanisms so decisions can be questioned and reviewed. And third, privacy conscious practices including data minimization and secure storage. Production-wise, I saved the preprocessor model and the threshold config for reproducible decisions. I include drift monitoring for key features like monthly charges and tenure with PSI as the next step, and I provide an inference API output that logs probability label and threshold used, model version, and time step, so predictions are auditable and monitorable. To wrap up, I built a validated Churn model with leakage-safe preprocessing and robust evaluation. I added interpretability with SHAP global and local explanations, plus PDP, ICE, and counterfactual actions to make the output actionable. For responsible AI, I performed a fairness audit using DP and equalized odds on senior citizen and gender, and I applied an evidence-driven mitigation with explicit trade-off reporting. I also documented ethical harms and practical safeguards, and I packaged the solution for deployment with saved artifact and inference API and a monitoring plan. Thank you.